Hey folks, yeah, let me just check if everything is working as expected. I'll be back in a while. Let me just check the audio quality. Uh, just let me, yeah, sounds good, folks. Yeah, we are live now. Let me just go through the live channel itself. Okay, some folks have already joined in. Somebody is asking, will it be okay to join the course from June after final semester exams get over? Triple IT Hyderabad exam results will come by then, and also many IIT selections list. Yes, Jaydeep, no problem at all. I'm assuming that you've already prepared for gate once. Since you've prepared once, you can always join the two batches that we're planning to start in the month of June. It's perfectly all right. Of course, you have shorter period of time. That's it, right? See, from June to Feb is going to be shorter period of time than May to Feb. That's all. But since you've already prepared once, it's perfectly okay. We can always cover up and we can always fill the gaps that we have and push you through practice. So that's not a problem at all. Just keep in mind that if you have a shorter period of time, you'll have to put in more hours every day. That's all. And yeah, thanks for joining in. So let's wait for a couple of minutes because it's sharp 7 right now. Some of you may see this audio jack that I have. So I was trying to find ways to reduce the noise during the live sessions, and I just came up with a jugaad or a hack to reduce the noise right now before we get something manufactured for this task. So just cooked up something offhand, and the noise reduction I believe is significant, especially with the fan and AC running at full throttle. I hope you're getting a good quality of audio now. Again, with the headphones and sorry, with the headphones and also this audio hack that we've done to avoid all the background noises as much as possible. It was a nice experiment for me. Anyway, so okay, somebody's saying I understood the concept, but I find it difficult applying in the test. Please suggest how to overcome this. Uh, yeah, frankly speaking, Mayank, that's a very common problem that many people come across. Okay, it's a very common thing. Understanding the concept is only 30% of the story. Being able to solve problems, it takes practice. To be honest with you, okay. Even when I was preparing for GATE, even today, right, I was solving the practice problems that you have in the practice test. It took me a while to solve some problems because it's been a while I solved these problems. Conceptually, I know all of these things. I've been applying them on a day-to-day basis as a machine learning scientist myself. But when it comes to gate problems, it requires a specific type of practice. Okay, that's what we're trying to do with these practice tests. If you need more practice, do let us know. We'll give you more practice tests, subject tests, etc. That's not a problem at all. The only way to be able to solve problems after understanding the concept is practice. There is no shortcut to that. Okay, to be honest with you, either you have to have that aptitude to solve problems, or you have to build that aptitude to solve problems by solving many problems. It comes only through practice, to be honest. Even I was a little shaky today when I was solving some of the practice problems, because some of the practice problems in this recent test are slightly hard, to be honest. It took me a while to it took me a while to figure out the solution, because I try to solve the problems without looking at the solution to see, so that I can guide students better on what are the challenges and how to think about the question. Some of the questions in this current practice test are non-trivial. Okay, I agree, but it's with practice that that you get around this problem. Okay, so so somebody is asking when the fourth batch is starting. It's best to just give us a ring. I think it's hard for me to answer all the questions in a live session. Then we can't do problems. So please just go to gate.appliedcourse.com. We have a phone number. Just call one of our teammates. Most likely one of the co-founders will lift the call and they'll give you detailed answers of all the basic questions that you have. Okay, it's perfectly okay to join at a later batch if you think that is more appropriate for you. That's perfectly all right, folks. Okay. So somebody is asking, what is the next subject? What is the next subject for after linear algebra? I wanted to talk about this. Shall we? Okay, let's do it. Since we're anyway 4 minutes into the discussion, I've written some notes here. So by Monday, which is 29th, right, we'll be done with linear algebra. There are a couple of things. There is diagonalization, there is LU decomposition, and Kelly-Hamilton's theorem. Just 3 theorems, just 3 concepts. We'll be done with that by Monday. Once we're done with that by Monday, 30th, please revise the concepts. On 1st and 2nd, we'll give you a practice test. Okay, since linear algebra is one small part of the whole engineering mathematics, we thought we'll give you one subject test. Let's finish the subject test by, you can take the test on 1st or 2nd. Okay, please take the subject test for linear algebra. From 3rd to 15th, we will be doing aptitude. And I'll tell you the reasoning why we are moving away from engineering mathematics to aptitude. There are a lot of students who now have exams. They've called us and said, Varma, your linear algebra is very good. We want to follow your course, but then it's hard for us to follow because we have exams around the corner. So they requested us to finish aptitude, which they can catch up later. Okay, so what we are planning right now is, since most universities and colleges will have their exams finishing by 15th of May, from 3rd of May to 15th of May, we'll have aptitude and reasoning. Okay, I think we've already uploaded 6 out of 9 chapters for aptitude, and we'll be uploading the rest of the 3 also soon. So all the content is already there. We have pre-uploaded the whole subject itself, so that you can go at your pace and finish it. And aptitude is something that you can do very fast. And we're doing it in this period of time when many students have exams, so that they can catch up with this subject later. I don't want to do something like, let's say, probability statistics or discrete mathematics, right? Because those are important subjects where there is a lot of marks coverage. Also, it is something that students may not be able to follow on their own without a schedule. Aptitude is, again, remember, aptitude is important. Please don't ignore it. Okay, I think from aptitude and English, you would get about 15 marks, and 15 marks is a hell lot of marks. That's the difference between a first rank and I think a 1000th rank. Okay, so 15 marks is a non-trivial chunk of marks. Okay, so aptitude is certainly important. It's very scoring, and it's also very simple. The aptitude in GATE is way simpler than if you take, let's say, aptitude in CAT exam, right? The other competitive exams like CAT, where aptitude is really, really hard. Okay, so as compared to that, the aptitude that we have in GATE is actually fairly straightforward. And we would do from 3rd to 15th, we would do aptitude. From 16th May onwards, we'll start engineering mathematics and discrete mathematics. Okay, so from 16th onwards, from 16th of May to be precise. Okay, so the 3rd to 15th of May, we'll finish aptitude. And those of you who can finish aptitude faster, there are other subjects, right? You can revise C programming, data structures, algorithms, or linear algebra. And we'll keep uploading more and more content for new subjects also. Already, I think 3/4, 6 out of 9 chapters for aptitude are already uploaded. And from 16th onwards, we'll restart engineering mathematics. So we'll finish all of engineering mathematics and discrete mathematics in one chunk. From May 15th, we'll try to do it as fast as possible. But what I need from all of you is, from May 15th onwards, we need to speed up. Okay, because your exams are over. I completely understand that for those people who have exams, we need to accommodate them. We respect that. But from May 15th, let's go full speed. Okay, we'll try and do maybe 3 hours of content every day, because it's vacation time for some of you. Those of you who are working professionals, we want to finish the content as fast as possible, so that we can spend more time in practice sessions and revision and things like that, right? So please understand that from May 15th onwards, we'll run at a faster speed, way faster than what we're doing today, or what we have done in the past for the other batches, right? We'll try and do maybe 2.5 to 3 hours of content every day, so that we can finish the bulky subjects, right? The bigger subjects faster. Okay, so any questions you have about this, again, we'll put in the schedule for aptitude in a couple of days. Any questions you have about this, please reach out to us over email, or please call us on the phone number on the website. We'll clarify any questions you have. In summary, 29th we'll finish linear algebra, 30th is for revision. 1st and 2nd, please take a subject test. From 3rd to 15th of May, we'll try and finish aptitude. From 16th onwards, we'll start engineering maths again. Okay, I hope this sequence of stuff is clear now. Sounds good. So let me share the screen so that we can get into. Okay, so let me share the screen itself. Sorry, so let me share the screen itself. Just a second. Okay, so let's get started with solving the problems. Okay, so let's take the first problem here. Let me hide this. Okay, so let's get started. So here it says, let A be a set of 3x3 symmetric matrices, all of whose entries are either 0 or 1. Okay, so it's a symmetric matrix. Look at this. It's a 3x3 symmetric matrix. 3x3 has 9 entries, right? It has 9 entries. Notice that this entry and this entry have to be same for a symmetric matrix. This and this have to be same, and this have to be same. Okay, now 5 of these entries are 1. So there are five ones, and 4 of them are 0. There are 4 zeros. Okay, the number of matrices possible. Okay, let's construct them. Okay, look at this. In the diagonal elements, so let's take the first case, right? There are two cases here. First case, the diagonal elements, let's assume the diagonal consists of 2 zeros. Look at this, the diagonal consists of 2 zeros, okay, and 1 1. Okay, and 1 1. Okay, so let's assume the diagonal consists of, first let's focus on the diagonal, then we'll talk about the off diagonal elements. Okay, so we only care about, so if you look at the diagonals, case 1 is I can have 2 zeros and 1 1. Okay, that's perfectly valid, right? And if I place 2 zeros and 1 1, in how many ways can I do that? Look at this, I have to place 2 zeros and 1 1, right? I can place this in 3C2 ways, because I have 3 positions and I need to place 2 zeros. In how many ways can I choose 2 positions out of 3 positions? 3 choose 2, right? And now in the remaining position, I'll place the 1. Okay, so I've already consumed 2 zeros and 1 1. What am I left with now? Look at this, I'm still left with 3 zeros and I'm left with 2 ones. Okay, I'm left with 2 ones. Remember that I need the 2 ones, because if I place a 1 here, so the 3C2 ways is for fixing the diagonal. Now I have 3 more positions here. Look at this, I have 3 more positions. Whatever value I place here, the same value I'll have to place here. So if I choose a value here, that value has to be fixed here. So there are only 3 cells that I'm still yet to choose. Okay, now look at this, I have 2 ones, right? Suppose if I place a 1 here, look at this, if I place a 1 here, the other one will anyway have to go here, right? Because this is a symmetric matrix. Or if I place a 1 here, this one is also taken up. If I place a 1 here, this one also will be taken up. Since I have 2 ones, I can only place 1 1 in these 3 cells. Rest of them have to be zeros. Okay, I hope this is clear. Okay, look at this, we have sorry, I have 3 ones left, right? One second, I'm consuming 2 zeros. One second, how many zeros and ones do I have? I have 5 zeros, right? I have 5 of them are 0 and 4 of them are, and 4 of them are, one second, let me just see. So 5 of these are 1 and 4 of them are 0. Okay, so 5 ones. Oh, there are 5 ones. Sorry, I'm reading it the other way around. Okay, let me just erase this. Okay, so let's do it more carefully. Okay, there are 5 ones, right? Suppose if I place 2 zeros, okay, and 1 1. Okay, let me write it actually. I think that's better. This is confusing. Okay, this is very confusing. So let me write it carefully. So I have 5 ones, right, and 4 zeros. So case 1 is going to be like this. Okay, case 1 is I'm going to place 2 zeros. I'm going to place 2 zeros, right, in my diagonal, and I'm going to place 1 1. I'm going to place 1 1 here. In how many ways can I place this? I can place this in 3C2. This is good. Now what am I left with now? Because 2 zeros are consumed, I'm still left with 2 more zeros. Okay, I'm still left with 2 more zeros, and 1 1 is consumed, so I'm still left with 4. I'm still left with 4 ones. Okay, there are 2 zeros left and 4 ones are left. Since I'm left with 2 zeros, let's assume I place a 0 here. I'm bound to place a 0 here again. Look at this, if I place a 0 here, I have to place a 0 here again. Okay, because this is a symmetric matrix, because the question says symmetric matrices. Now if I placed 0 0, these 2 zeros are already taken up, right? I'm still left with 4 ones, which means I'll place 1 1 here, which means I have to place 1 1 here. So in how many ways I can place this 0? Once I've fixed this 0, the rest of the ones location is fixed. So in how many ways can I fix this 0 location in these 3 cells? Amongst these 3, I need to choose 1, right? So there are 3 choose 1 ways of fixing the 0, right? So in how many ways can I place? So the total number of symmetric matrices that I'll have. Okay, again, we'll see all of this in counting again. Okay, when we learn discrete mathematics, we'll again learn some of these things in counting. But we placed this question here because all of you may have learned 3n choose k in your 11th and 12th class mathematics, right? That's why we have placed it here, right? Now in how many ways can I place this 0 here? I can place it in any one of the 3 locations, right? So that's why 3C1. So that in case 1, where I have 2 zeros, on the diagonal and 1 1 on the diagonal, and rest everything are off diagonal, I have 9 ways of doing it. Okay, this is case 1. Let's look at case 2 now. Okay, case 2 is I have all ones. I have all ones on the diagonal. I have all ones in the diagonal. Okay, so the diagonal consists of 3 values. So 1, 1, 1. I've already taken 3 ones. How many values am I left with? I'm still left with 4 zeros. I'm left with 4 zeros because 3 ones are taken up. I'm still left with 2 ones. Okay, so see, these 3 values are already taken up, right? I have 2 ones, and as we have seen, if I place a 1 here, I'm bound to place a 1 here because of the symmetric property of this nature. Okay, so since I have 2 ones and 4 zeros, and I have these 3 places to fill, half of these zeros will be placed here, half of them will be placed in this lower triangular part. Okay, half of these ones will be placed here, half of them will be placed here. So let's assume, so now what do I do? I have 3 locations. I have to place 1 1 there. So 3 locations and 1 1. How many ways can I do it? I can do it in 3C1 ways. Okay, I can do it in 3C1 ways, right? Now if I pick, suppose I placed my 1 here. Okay, I'm bound to place my 1 here. Then rest 4 zeros that I'm left with will be by default placed here. So there are only 3 ways in which I can construct symmetric matrices with 5 ones and 4 zeros, right? So in case 1, I have 2 zeros and 1 1. Case 2, I have all ones, right? There are 9 ways here. There are 3 ways here. Let's write case 3. Okay, case 3 is all zeros. Case 3 is all zeros. Is that even possible? If I place all zeros here, look at this. Look at this. Look at this. I have 9 slots here, right? I have 9 slots here. Okay, if I place all zeros here, I'm left with 1 more zero here, right? Now if I place the 0 here, I don't have a 0 to be placed in the symmetric location. Similarly, I have 5 ones here. See, 5 is an odd number, right? But what I have, look at this. But if you think about it, I need an even number of ones for symmetric nature, because whatever I place here, I need to place it again here. So all zeros on the diagonal is not possible. Case 4. Okay, just 1 0. Just 1 0 on the diagonal. Is that possible? Let's try it out. Okay, if I place 1 0, okay, again 3 3 3 3 3 3. If I place 1 0 on the diagonal, okay, 3 more zeros are left which have to be off diagonal, right? And 3 is an odd number, right? Suppose if I place 0 0 here, the other 0 I place here, I don't have a 0 that I can place here, right? The same problem will occur even with ones. If I place 2 ones here, I'm left with 3 more ones. Where will I place those 3 ones now? The symmetric nature will break up. So case 3 and case 4 are not possible. Only case 1 and case 2 are possible. For case 1, I get 9 matrices. For case 2, I get 3 matrices. Total, I get 12 matrices. Okay, this you have to be careful. Again, this is not a trivial problem. This is slightly on the harder side, to be honest with you. Okay, because it takes time. You have to go through each of these cases and think through very, very carefully. Okay, even if you miss any of these cases, you'll make mistakes. Okay, this problem is error prone, and this problem, actually, the good part about this problem is it is combining concepts from linear algebra and from simple combinatorics. Okay, simple combinatorics like 3C2, like n choose k. So these problems are actually very interesting because they test your skills in more than one area of mathematics. Okay, so I hope this is clear. Some of these questions are tricky, to be honest with you. Okay, so now let's look at another question here. Okay, let P be a matrix of order 4 cross 4 which satisfies this characteristic equation. Then the product of eigenvalues is, okay, look at this. P is a square matrix of size 4 cross 4. If you have a 4 cross 4 matrix, what should the characteristic equation look like? Look at this. If I have a 4 cross 4 matrix, okay, if I have a 4 cross 4 matrix, okay, some 4 values here, what is the characteristic equation? A minus lambda I det equals to 0. Which means the minus lambda will be here, the minus lambda will be here, the minus lambda will be here, the minus lambda also will be here. Which means what should the characteristic equation look like? The characteristic equation should have the 4th polynomial. Here you have only the 3rd polynomial, right? How should the characteristic equation look like? Let's assume your x is nothing but your lambda. Okay, your x is same as lambda here. Okay, how should your characteristic equation look like? Your characteristic equation should look like ax4 plus bx cube plus cx square plus dx plus e equals to 0. It should be a polynomial with the highest order being 4. But what do we see here? We see only a polynomial of order 3. So this is a tricky question. Okay, which means if the characteristic equation is like this, it satisfies this equation. See, the characteristic equation satisfies this equation. Okay, but this is the highest order here is 3. While for a 4 cross 4 matrix, if you actually write a minus lambda equals to 0, you should get the fourth polynomial, right? You should get the polynomial with exponent 4. So if this is what I have x cube minus 5x square minus 8x plus 48 equals to 0. Now, see, because your matrix satisfies this, which means if I want to convert this into the standard form, see, this is the standard form, right? Because I have minus lambdas here, or minus x that we have. Okay, so if I multiply both sides by x, what happens? X power 4 minus 5x cube minus 8x square plus 48x plus 0 equals to 0. Is this fair? Now, if you notice, this is in the standard form for a 4 cross 4 polynomial. Okay, for a 4 cross 4 polynomial, we should have the fourth exponent. And now we have the fourth exponent now. Okay, now this makes sense, right? So what have I done? I've just multiplied both sides by x to get the fourth polynomial. Now, when I get if this is a characteristic equation, look at this. This is a characteristic equation, right? Now, if you notice, what is the solution of this characteristic equation? A very simple solution. A very simple solution of the characteristic equation is x equals to 0. This is a characteristic equation, right? Which means one of the lambdas, which means I have a lambda which is equal to 0. So I have an eigenvalue, right, which is equal to 0. One of the eigenvalues is 0. Now the product of, what will happen to the product of eigenvalues now? If one of the eigenvalues is 0, the product of all the eigenvalues will also be 0. Okay, so this is a tricky question. Okay, people often misread, people don't read this 4 cross 4 carefully, right? So whenever you're given a characteristic equation, it should be in this standard form. If it is not, convert that into standard form, and then you can compute the possible values of lambda. Okay, again, this is a tricky question, not a hard question. Okay, sounds good. So let's go to the third question now. This is a tricky question. This took me a while to solve, but it's not hard actually. It requires a subtle leap actually. It took me a while to figure that out. So you have this matrix equals to this complex looking matrix. Okay, and you're given that AB minus CD equals to K. Look at this. You're given AB minus CD equals to K. Okay, the question here is what is the range of K? Now, the moment I see this, it took me a while to figure out. So look at this. AB minus CD equals to K. What does that mean? So if I write this as a matrix determinant, AB, and I can write CD like this. Okay, so if I have a matrix which is ABCD, look at this, AB minus CD, this determinant equals to K. Now, if you notice, this is the trick. This is, I should say, this is the part that took me a while to figure out. If this matrix is A, if matrix A is ACDB, this matrix that we have is actually A square. You can verify that. If you try to compute A square, okay, if you try to, so this took me a while to figure out. ACDB multiplied by ACDB. Okay, so whenever, and the way I came to this conclusion, that's the more interesting part. The moment I saw this, I felt, okay, this looks like a determinant of a 2D matrix. So I actually wrote the 2D matrix. Then I said, if this is the 2D matrix, because this is the information that is given to us, right? If this is the 2D matrix, A square must look like this. And I verified that. Look at this. A square will have AC plus CD as the first, A square plus CD as the first element. What is the second element? AC plus CB. AC plus CB is the second element. The third element is DA plus BD. DA plus BD. The fourth element is DC plus B square. Right? So this is your A square. Now, one more leap that I had to make was this is now A cube. You can again verify this. Okay, it took me a second to figure that this is A square and this is A cube. Now, what is this equation telling us? This equation is telling us if this is matrix A, the determinant of A is equal to K, and A square equals to A cube. That's what this equation is saying. This equation is saying A square equals to A cube and determinant of A equals to K. Then what is the value of K? Okay, so now let's simplify this. Okay, Can I write this as a cube minus a square equals to 0? I've just taken a square to the other side. So let's take a square out. A square, this is equal to 0, right? If this is equal to 0, look at this. If this is equal to a 0 matrix, look at this. This is equal to a 0 matrix. When will this be? When will this be equal to a 0 matrix? If this will be equal to a 0 matrix if A is a 0 matrix or A is equal to I. Look at this. I have a square. See, a square has to be 0 matrix or a minus I has to be 0 matrix for this whole thing to be a 0 matrix. There are only two possibilities, a equals to 0 or a equals to I. If a equals to 0, what is det of a? Det of a equals to 0. If a equals to I, det of a is equal to 1. So your k can either be 0 or 1. There are only two possibilities, which means your a can lie only in this interval 0, 1. Okay, so this is a tricky problem. Okay, this problem is, I would actually rate this problem as hard. Not this is slightly above the gate level, to be honest. Okay, because this requires you, this is certainly above the gate level, because coming up with this is easy. Okay, so as soon as I saw this, I came into the matrix form, but figuring out that this is a square and this is a cube took me a little while to figure out. Once I got that, the whole mathematics was placed. Again, it is by design that we gave a slightly harder practice test this time, so that you are prepared even for the worst case gate exam. Okay, where the question paper is rock solid hard. Okay, we want you to prepare for all eventualities. Okay, so let's look at this question. Okay, this is also a good question actually. Okay, again, this is slightly tricky, but it's not very hard. Okay, it took me a couple of seconds. Again, some of these problems are tricky, but they're not hard. Okay, so you have this matrix A and it says trace of A is less than equal to 16. Then the maximum value of the determinant. Okay, what is the determinant? Determinant is xy minus 16. This is the determinant. Okay, now it says trace of A is less than equal to 16, which means x plus y is less than equal to 16. Okay, now what do I want? So this is my det of A, right? So this is my det of A. So it says what is the maximum value of the determinant? So I need something like this. I need xy minus 16 is less than equal to some value. When I can get this inequality, see, I have this inequality and I want to get an inequality like this, because now I can say that the maximum value of the determinant will be whatever I have on RHS here. Now, if you have x plus y and you want to get it in terms of xy, what do you do? Okay, there is this very simple thing that you probably learned in your 11th and 12th class, that the geometric mean of two numbers is less than equal to the arithmetic mean of two numbers. Okay, again, I can prove this for you. Okay, if you want, I can actually prove this for you. Just a second, folks. Sorry, xy plus 16. I'm sorry, xy plus 16. I'm sorry. Okay, sorry, xy plus 16. My bad. Okay, xy plus 16. Okay, thanks Naveen for correcting me. Thank you. So it's xy plus 16. I'm sorry. But see, look at this. I have an inequality with x plus y and I want something with xy. Okay, for this I need to prove. See, if you've forgotten this, right, I can prove this to you. I can actually prove this to you. Let me actually show it to you. Actually, I've forgotten this. I didn't recall this at the top of my head, but then I figured it out. For example, if x and y are two numbers, right, then x minus y whole square is greater than equal to 0, because the square of any number is greater than equal to 0, right? And x minus y whole square can be written as x square plus y square minus 2xy, right? Which I can write it again as x square plus y square plus 2xy, because I want to get x plus y whole square minus 4xy. I can write it like this. Now this term, I can write it as x plus y whole square minus 4xy. Okay, so now can I write this as 4xy is less than equal to x plus y whole square? If I take square root on both sides, what do I get? I get x square less than equal to x plus y by 2. Okay, this is your GM less than equal to AM inequality. Okay, this is your GM less than equal to AM inequality for two numbers. I've just proved it, right, with simple algebra using just x plus y whole square and x minus y whole square formulae. Okay, actually I didn't recall this, so it took me a second to figure that out. And now the moment you figure out that GM is less than equal to AM, and you can use this, right, because GM is less than equal to AM, can I write this as this? X plus y by 2 is less than equal to 8. This is the AM. This is arithmetic mean of these two numbers, right? And we know arithmetic mean is greater than equal to geometric mean, which is square root of xy. Now what do I have? I have square root of xy is less than equal to 8, which means xy is less than equal to 64. If x, look at this is a form that I want, right? See, that's the trick. When you have to solve a problem like this, you have to look at all the formulae, all the theorems, all the mathematics, and try to figure out a relationship here. That's what is the mathematical problem solving skill. Okay, if xy is less than equal to 64, then xy plus 16, then xy plus 16 is less than equal to 16 plus 64, which is 80. So the maximum value of the determinant is going to be 80. It's a fill in the blank, and the answer here is 80. Okay, again, this is a slightly tricky problem, and the moment you see xy here and the moment you see x plus y here, it should strike to you that yes, I can convert this, the sum I can convert into arithmetic mean, product I can convert into geometric mean, and this should strike your head immediately. Okay, slightly tricky problem, but it's doable. Again, as I've told you, by choice we have given some slightly interesting problems this time. Okay, so now let's go and solve this. If P be a matrix of order 2 cross 2, it's a 2 cross 2 matrix. So it will have A, B, C, D. Okay, it's a 2 cross 2 matrix. Trace of P equals to 5. What does it mean? A plus D equals to 5. A plus D equals to 5. And det of P equals to 4. What is det of P? Det of P is AD minus BC equals to 4. AD minus BC equals to 4. Yes. Okay. Then the smallest value of the smallest eigenvalue of P inverse. Okay, this is going to be tricky. Okay, this is your P, right? Again, this is, see, you're given these two equations. You'll have to make use of them. In a nutshell, that's what. See, you're given these two equations because you have to make use of them. What is P inverse? If this is your P matrix, how will P inverse look like? We have seen a two-dimensional example, right? For a 2 cross 2 matrix. What is the det of P? Det of P is given as 4, right? So it will be det of P, adjoint of P. Adjoint of P by det of P, right? What does adjoint look like? D will come here. This will become minus B. This will become minus C, and this will become A. So P inverse will look like this. This is the adjoint of P. Again, for a 2 cross 2 matrix, it's easy to put this. For a 3 cross 3 matrix, it will get tiring. And remember that we are already given det of P equals to 4, which I'm using here, right? So this is what your P inverse will look like. Now, what does it say? What is the smallest eigenvalue of P inverse? To compute the eigenvalue of P inverse, if you write the characteristic equation of P inverse, it will look like this, right? P inverse minus lambda I, det of this equals to 0. This is how it will look like, right? Right? Now, if you look at this, this is what I have. Okay. So what is the, so what is P inverse minus lambda I going to look like? It's going to look like D by 4 minus lambda minus B, right, minus C, sorry, by 4 minus lambda, this det is equal to 0. Okay, this is a characteristic equation of P inverse, right? This is a characteristic equation of P inverse, very simply speaking. So if this det is equal to 0, what does this mean? Numerically speaking, this is D by 4 minus lambda into A by 4 minus lambda, right, plus minus, there is 2 minus here, right? So minus BC by 16 equals to 0. This is what we have. Now look at this. I already have A plus D value. I have AD minus BC value also. Now let's try and use these values. Okay, so we have to modify this equation. Okay, because you're given these two equations, we have to modify this equation in such a way that I can use A plus D and AD minus BC, because I'm given these values, right? Now I want to compute the value of lambda given that these two equations are true. And this is where you'll have to play some geometry. Okay, so the geometry that we can play here is, if you can modify this actually. If you simplify this whole thing, you can actually write this as 16 lambda square minus 4 lambda. And while modifying this, the only thing I was trying to do is I was trying to get everything in the form of A plus D and AD minus BC. That's what I was trying to get. Okay, because I know these values, I can plug these values immediately, right? So while simplifying this, the only thing that I kept in mind is I want to get this term A plus D somewhere. So if you're careful with that, you'll get A plus D here, and you'll get plus AD minus BC. So if you simplify this, again, when you are simplifying, because we have these two equations already, we have to convert this equation into this equation, wherein we are using A plus D and where you're using AD minus BC, so that we can plug in these values, right? So when I plug in these values, the whole equation will become 16 lambda square minus 4 or 20 lambda, right? Minus 20 lambda plus 4 equals to 0. Okay, I can divide the whole thing by 4 and I'll get 4 lambda square minus 5 lambda plus 1 equals to 0. And if I simplify this, if I just solve it, right? I hope you recall Sridharacharya's formula, right? If you have ax square plus bx plus c equals to 0, a quadratic equation, okay, this is something that we probably learned in 8th or 9th grade, right? So this is a quadratic equation. There is something called as Sridharacharya's formula. Sridharacharya's formula. I don't know if many teachers teach that this is called Sridharacharya's formula. He's a phenomenal mathematician from the Kerala School of Mathematics in India, who actually came up with a solution, a closed form solution for this, right? So this is equal to minus b plus or minus b square minus 4ac by 2a. Am I right? 2ax. Okay, if I square both sides. Okay, yeah. So this looks like it. Yeah. So if I square both sides, I'll get, yeah, this makes sense, right? So using this closed form solution for quadratic equations, I can solve this quadratic equation and I would get lambda equals to 1 or lambda equals to 1 by 4. Okay, and what are these lambdas? These lambdas are eigenvalues of P inverse. Remember that these lambdas are eigenvalues of P inverse. The question here is, what is the smallest eigenvalue of P inverse? P inverse has only two eigenvalues, 1 and 1 by 4. The smallest is 1 by 4. So you can put in your answer as 0.25. Okay, again, while solving this problem, okay, we have to be very, very careful, especially the big leap. This is the big leap. It's easy to reach till here. Okay, till here it's perfectly valid. From here to reach to this simplification, this is the big leap. This is a mathematical intuition that you have to build. Okay, you have to always try to convert this into terms that we already have, as I've just mentioned. That is the critical aspect when you're solving problems like this. Okay, so okay, the fifth problem is also done. Let's go to the sixth problem. Okay, yeah, the sixth problem is here. So this is a relatively easier problem. So let's go and tackle this. You're given a matrix A, you're given a matrix P, and you're told the trace of A equals to 5. And you're asked what is the trace of P inverse AP. Okay, very good. Look at this. This is a 3 cross 3. This is 3 cross 3. I'm, of course, we'll have to compute it. Again, look at this. I'm given A and B here. I'm not given any values of what A and B are. But let's use some simple properties, right? We have seen this. Trace of AB equals to trace of BA. We've seen this property, right, in the course videos. So now can I write trace of P inverse AP? How can I write this? If you think of this as one matrix and this as the other matrix, can I write this as trace of AP into P inverse? Trace of AB is trace of BA, right? Now look at this. Instead of having this AP multiplication, I can write it as PP inverse multiplication. PP inverse is anyway identity matrix. A into identity matrix is A itself. So this is equal to trace of A. And we are given that the trace of A is 5. Right? So we are given the trace of A equals to 5. Right? So trace of P inverse AP is also equal to 5. Okay. So in general, if P is an invertible matrix, then trace of P inverse AP, as long as you can multiply all three of them comfortably, equals to trace of A. This is actually one of the properties of trace, which we did not cover in the course videos, hence we gave this problem. Okay, and this is very simple. All you need to know to prove this is trace of AB equals to trace of BA. If you know this, this is a trivial expression. Okay, sounds good. So this is a more easier problem. Okay, so now let's go to the seventh problem here. Okay, so this is going to get exciting. Oh, okay. This is a good problem actually. Suppose we have a following matrix A, which is the augmented matrix. Okay, for a linear system of equations. What is an augmented matrix? This is, so if I have a linear system of equations as AX equals to B, this is my A and this is my B. That's what an augmented system of equations mean. Now the number of values of A that can make the above system consistent. Now what is consistent? We have seen this, right? What is a consistent system of equations? Consistent means there exists some solution. It could be exactly one solution, or it could be infinitely many solutions. Okay, but there should exist some solution. That's what it means. Okay, inconsistent basically means there is no solution. Okay, so now let's look into this. Okay, so for it to exist, for it to have at least one solution or infinitely many solutions, there is something that is needed. Look at this. So we have seen the 2D example, right? We have seen the 2D example in the course videos, if you recall. Okay, wherein I said if you have two equations of lines like this, okay, how will the equations of these two lines look like? This will look like 3x plus 2, 3x plus 2y equals to 6, and the equation of this line will be 3x plus 2y equals to 12. Now if you notice, these two equations, the coefficients are exactly the same. It is only the RHS that is differing. Or in other words, or I can write this equation also as, okay, I can also write this equation as 6x plus 4y equals to 24. Now if you notice, 3 into 2 is 6, 2 into 2 is 4, but 6 into 2 is not 24. So on the RHS part, on the AX equals to B, on the LHS part, each of the rows are linearly dependent, but the same dependence or the same relationship between the rows is not happening on the RHS. Then you'll have two parallel lines, right? In 2D, I showed this example, right? I think I showed this in the video where I discussed consistency itself, right? If you have two lines like this, when are they parallel? When these two coefficients, 3 into 2 is 6, 2 into 2 is 4, but when this does not match, then you get two parallel lines and this system is inconsistent, right? This is when you get, so geometrically speaking, this is where you get inconsistent system of equations. Okay, now to solve for the so to think about it, so one way to think about it is, let's reduce this whole thing. Okay, let's perform, because here on the LHS front, right, I can just perform row operations, elementary row operations. So on this whole matrix, I'll start performing row operations one by one. Okay, since there is less space here, let me actually do it here. Okay, so let's write the matrix here. I'll show you how to solve this problem. It's actually very simple if you have understood the geometric interpretation here. Okay, so this is what we have. We have 2 minus 1 minus 2 a square, minus 1 minus 7 minus 11 and minus a. Let me just check. 1 2 minus 1, 2 minus 1 minus 7, 3 2 minus 1. Yeah, this is what we have. Now let's try to convert this into the Echelon form. Okay, to convert into Echelon form, first I'll try to make these two equal to 0. Okay, I can easily make these two equal to 0, right? Multiply this by 2, subtract it from this. Okay, so my first row will remain the same. My first row will remain the same. I'll try to make these two values 0. When I try to make this value 0, I'll get, again, I'm not showing each of the steps because you know how to apply the elementary row transforms. We have seen tons of examples of that, right? Just in the interest of time, I'm skipping that part, right? So you get a square minus 2a cube minus 2. Similarly, how can I make this 0? This plus this, I'll make it 0, right? So this will become 0, this will become minus 5, this will become minus 8, and this will become minus a plus a cube plus 1. Okay, because we're just adding row 1 and row 2. Okay, now I will try to convert this to 0. Okay, because I've converted these, because I'm trying to convert it into Echelon form, right? Look at this. I'm converting this part as well as this part, because I'm just performing elementary row operations to understand if these linear system of equations, if these rows, right? Look at this. If these columns and rows represent these lines which are parallel, that's what I'm trying to find out, right? Right. So now if I apply row transformation again, what happens now? Okay, so these two are same, these two are same. So what will happen now? So this will become like this, a cube plus 1. This will remain 0, minus 5, minus 8, a square minus 2a cube, right? Sorry, a square minus 2a cube minus 2. That's true. So this will become 0, this will become 0, this will become 0. This minus this, right? And I'll get minus a plus a cube, right? Plus a cube plus 1 minus a square plus 2a cube plus 2. Okay, if you notice, this whole third row has become equal to 0 after elementary transformations, which means this third row can be expressed as a linear combination of the first two rows. Forget about this part. So in my original matrix of AX equals to B, right, I have 3 rows, right? So in these 3 rows, I can represent the third row as a linear combination of the first 2 rows. which means on the B side also, on the B side, because all of them have become 0, this also has to become 0. If this doesn't become 0, we'll end up with a case where this whole thing becomes parallel lines and there is no solution, because we want it to have to be consistent, which means we want it to have some solution. So whatever linear operations we've applied, sorry, whatever elementary row operations that we've applied on this part and this part, we applied the same thing even on the augmented part also. Now, if this part is not equal to 0, look at this. Look at this case, right? If this is multiplied by 2 and this is multiplied by 2, when I multiply this with 2, I should get this. Only then they both are not parallel lines. Okay, multiplication is the simplest form of elementary row transformation. Here we have done more complex elementary row transformations. So this has to be equal to 0 for your linear system, for your system to be consistent. Okay, if this is equal to 0, look at this. This has to be equal to 0. Now, if you solve this, you can simplify this and solve it. You'll get that one of the solutions for this is a equals to 1. That's one of the solutions that you'll get. Okay, and that's the only real solution that you'll get. Okay, all other solutions that you'll get will consist of imaginary numbers. Okay, so the only real valued solution you get is a equals to 1. And what does the question say? The number of values that a can take. Okay, I'm hoping here it says a is a real value here. Look at it, it says a belongs to R, which means a belongs to a set of real numbers. There is only one value of a, which is equal to 1 itself, wherein this system becomes consistent. Okay, the key idea is for a system to be consistent. The key idea here is for a system to be consistent. Okay, the linear transformations on each of the rows that you apply for your ax equals to b. Okay, the linear transforms that you apply here, the same linear transforms if you apply here, the equation should match. So here, for the case of parallel lines, the simplest linear transformation that the simplest row transformation or elementary row transform that we applied is simple multiplication. Okay, this is a very, very important concept about consistency in general and how to test for consistency. Okay, so now let's go to question 8. Okay, so let's see what this question says. So consider matrix A, which is an equals to this. Let P be an into an minus 1 so on up to a2, and trace of P is 480. Then what is the value of n? Okay, this is like a tedious one if you think about it. Now what is an? What is an into an minus 1? Let's write this. Okay, so if you can actually compute this, what is an into an minus 1? An is this. Okay, this is your an. What is an minus 1? N minus 1, 0, 1 and n. Now if you multiply both of them, you get n into n plus n into n minus 1 here. Okay, look at this. We are only given trace, so we only care about these two elements. We don't have to care about the rest, to be honest. Okay, because this is the number that I'm given and I have to find n, right? So this term is going to be n into, so 0 into 1, n into n minus 1. What about this term? The rest of the terms I don't care for trace. Okay, so what is this term going to be? This term is this row multiplied by this column. 1 into 0 is 0, n plus 1 into n. N plus 1 into n. Now I can repeat the same process. Okay, again I can fill in these terms also. So if you fill in these terms, this will be 0 and this will be 2n. Okay, if you now perform an into an minus 1 into an minus 2. Okay, again simple matrix multiplication with the variables, you will end up getting n into n minus 1 into n minus 2 here. Okay, you will get 0 again here. You'll get some expression here. What you get here, because we care only about these two terms, what you get here is n into n plus 1 into n minus 1. Okay, this is what you get for 3 terms. Okay, if you keep going on till a2, okay, you can actually extrapolate from this. If you keep going on till a2, the terms that you get here, because that's what the trace is, right? The terms that you get here, if you keep going on from an up to a2, okay, if you multiply everything, the term that you get here is going to be n. See, look at this, an minus 2. So you have n up to n minus 2. So if you keep going on till 2, what happens? This will be n into n minus 1 into n minus 2, so on up to 2. What is this? This is nothing but n factorial, right? What about this term? If you look at this term starts with n plus 1. Okay, then I get n. Okay, but If I'm multiplying a n minus 2, I'm only getting one less than that, which is n minus 1. This is n minus 2, but I'm getting n minus 1 here, right? So if I keep going on, I'll get up to 3 here. Look at this. If I have n minus 2 here, I'm getting n minus 1. So if I have 2 here, I'll get 1 greater than that, which is 3. So this expression is going to be n plus 1 factorial by 2, right? Because there is no 2 here, right? So now the sum of these two terms, look at this, sum of these two terms equals to 480. Okay, the sum of these two terms is equal to 480. So now when I write it, what do I get? N factorial plus n plus 1 factorial by 2 equals to 480. Now let's try to take out n factorial out of this. 1 plus n plus 1 by 2 equals to 480. Okay, what does this imply? What do I get from this? I get n factorial into n plus 3 by 2 equals to 480. Now try n equals to 1, n equals to 2, so on and so forth. Okay, because the very fact that factorial exists means that they have to be integers. Real numbers don't have factorials, right? So they have to be integers. The moment I saw a number like 480 here, which value of n, see 5 factorial. Look at 5 factorial here, right? What is 5 factorial? 5 into 4 into 3 into 2 into 1, which is 120, multiplied by 5 plus 3 by 2. Okay, I just tried out n equals to 1, n equals to 2, n equals to 3, 4, 5. Okay, so n plus 3 by 2, 8 by 2 is 4. So this is equal to 480. So the value of n here is 5. Okay, requires a little bit of mathematical tweaking, but this is not a very hard problem. Okay, so this you can expect in some of the, from a gate standpoint, this is slightly hard, but not too hard again. Okay, sounds good. So now let's go to the 9th question. Okay, this is a good question actually. So you have these 3 vectors, right? You have 1 minus t, 0, 0. This is one vector that you have. The other vector that you have is 1, 1 minus t and 0. The third vector that you have is 1, 1, 1 minus t. They are linearly dependent. Look at this. It says that these 3 vectors, these 3 row vectors are linearly dependent. Then what is the value of t? The very fact that they are linearly dependent means that their det is equal to 0. That's what it means, right? What does linear dependence mean? The area of the parallelepiped is going to be equal to 0, right? And the det of A and det of A transpose is the same, right? So now from that simple concept of linear dependence and area of parallelepiped and determinant, right? Very simple concept that we've already learned about. So this det has to be equal to 0. Now if you write this det, you'll get 1 minus t into 1 minus t into 1 minus t. Rest all the terms will be zeros. This into this minus 0. This is 0. So anything that you multiply and add will be 0. This is 0. So anything that you multiply and add will be 0. So this is equal to 0. What does this mean? This means t equals to 1. Right? What is the solution for this expression? 1 minus t cube equals to 0, which means t equals to 1. So the answer here is very simple, 1. So all that you have to know here is, see, what you have here is actually a lower triangular matrix. Okay, because the upper triangular elements are 0. Okay, and all you have to know is, if these vectors are linearly dependent, then if I write them like this, their determinant should be equal to 0. That's all there is. Okay, this is a simpler, straightforward question. This is the types of question that you typically can expect in GATE. Okay, so this is a good one. This is slightly time taking, but it's fun. Okay, inverse of an involutory matrix. What is an involutory matrix? So let's take this expression. What is an involutory matrix? We have already studied this, right? A inverse equals to A is an involutory matrix. So inverse of an involutory matrix is itself. Okay, 0 minus plus 1, it's an involutory matrix, yes. So A will match with 3. Okay, idempotent matrix, identity matrix, no. So A will match with 3. So this is option right, this option is right. This can't be right and this can't be right. I'm just trying to eliminate for speed. Okay, the next point is determinant of an idempotent matrix. What is an idempotent matrix? Idempotent matrix is A into A is A itself. Applying the linear transformation twice gives you the same linear transformation. So if I take det on both sides, look at this. If I take det on both sides, what do I get? I get det of A into det of A equals to det of A. Okay, when will this be true? When det of A equals to 0 or when det of A equals to 1. These are the only two possibilities, right? These are the only two possibilities. So determinant of an idempotent matrix is either 0 or 1. Okay, so B will match with C. This is also doing it, this is also doing it. Let's take C and then we can solve this problem. Inverse of an idempotent matrix. What is an idempotent matrix? A into A equals to A. This is an idempotent matrix. Now I want to compute the inverse of it. Now let's assume A has an inverse. Okay. So idempotent matrix can have a det of 0 or a det of 1. Let's assume that this idempotent matrix has a det of 1. Let's assume. Okay. So now what can I write? I can post multiply both sides by A inverse. When I multiply both sides by A inverse, I get AI equals to I. Look at this. This becomes I. This becomes I. So I get AI equals to I. So this looks very similar to A into A inverse equals to I. So what is the definition of A inverse? A inverse is that matrix with which if you post or pre-multiply, you will get the identity matrix. Which means, because this is the definition of what an inverse of a matrix is, because of this definition, and because AI equals to I, A inverse of this involutory matrix, sorry, A inverse of this idempotent matrix, sorry. Okay, because this is idempotent matrix. Okay, the A inverse of this matrix is I itself, right? So for C, option is identity matrix. So C5, that's it. So option B is the right option because option C is no more valid. But let's look at the other two options also, because I just want to show it to you. What is the determinant of a 9 cross 9 skew symmetric matrix? Okay, this is a very good question. So what is a skew symmetric matrix? Let's look at it. A skew symmetric matrix is this. This is a skew symmetric matrix, right? Now, what does it say? I have a 9 cross 9 skew symmetric matrix. So the det of this equal to det of this. This is a 9 cross 9 matrix. So if I take -1 outside, look at this. You remember this, right? Constant multiplied by a matrix, the det of it. Okay. So this constant will come out. This will be raised to the power 9, right? And det of A equals to det of A transpose, right? And det of A transpose is nothing but det of A. We know this as a property. So what do we have now? We have -1 to the power 9, det of A equals to det of A itself. See, -1 power 9 is -1, right? -1 power 9 is -1. And det of A equals to det of A. What does this imply? The det of A has to be equal to 0, right? Otherwise, this equation is never true, right? So now D will match with 1. Okay, again, I'm just proving each of them for you. These are very simple proofs. If you know the properties, they're just 2-line proofs. Okay, next question is determinant of an involutory matrix. What is an involutory matrix? A inverse equals to A. This is the involutory matrix, right? The inverse of the matrix, inverse transformation is same as the same transformation. That's why it's called involutory. Now let's look at it. Now, what is the only option left? The only option left is this. It says determinant of this. Okay, let's take the det of both sides. Let's take the det on both sides, right? Now, the det of A inverse, right? So if det of A is A, let's assume it is A because it's a number. What is det of A inverse? It is going to be 1 by A, right? Det of A inverse is 1 by A if A inverse exists, right? Because again, you can argue about this geometrically. Okay, if A is making a transformation which is making the area of the parallelepiped or the volume of the parallelepiped increase by A, the inverse of it will shrink it. That's how I remember this. Again, I remember this. I remember that if det of A is X, det of A inverse is 1 by X. I remember it from the geometric perspective. I don't remember the formulae. I'm very bad at remembering formulae. I try to remember things from a geometric standpoint. Okay, that we have discussed in the course videos, by the way. Okay, so if this is true, then what does it mean? It means A square equals to 1, which means A equals to plus or minus 1. That's why you have E2. Again, all these are just 2-line proofs. Very simple, very elegant stuff. So option B is the right option here. Again, we could have solved it by just looking at the first 3 options without going into the 3rd, 4th, and 5th also. Okay, so this is an interesting question because it is testing lots of concepts in a single question. Okay, these questions are tricky, but they're fun. Okay, so now let's look at this. If a matrix of coefficients, if the matrix of coefficients of a homogeneous system, what is a homogeneous system of equations? Ax equals to 0. Okay, if it has an inverse, so A has an inverse. Okay, what does it mean? See the coefficients, this is the coefficients, right? It has an inverse. What does this imply? This implies det of A is not equal to 0. Then the system does not have infinitely many solutions. Let's see. Again, we've seen this in the course videos, right? We have seen that if det of A is not equal to 0, then If det of A is not equal to 0, we have said that it has no non-zero solutions. It has only the trivial solution. It has no non-zero solution. It only has trivial solution. Only when det of A equals to 0, then you have infinitely many solutions for a homogeneous system of equations. Again, we have written this very clearly we have explained this very clearly in the course videos. So what does it say? What does it say? It's coefficients, blah, blah, blah. Then the system does not have infinitely many solutions. Yes, this statement is true. It's always true, right? Because if det of A is not equal to 0, it has only one solution, which is a non-zero solution, right? So this is always true. Very simple question. If you just know this property, just directly apply that. Okay, very, very simple question. Now let's go to question 12 now. Okay. Okay, let's see what this says. This says this is a linear system of equations where A, B, C are non-zero and non-unity. Unity basically means 1. Okay, and this system has a non-trivial solution. Then what is the value of this? See, the moment somebody asks you this, right, you have to convert everything into this form. That's the lesson. Okay, now let's write the matrix here, right? So if I write this as AX equals to 0, if I write this as AX equals to 0, and it says it has a non-trivial solution, it's a homogeneous system of equations. What does that mean? It means det of A equals to 0. We've just seen that, right? If det of A is not equal to 0, then it has only the trivial solution. But the fact that it has a non-trivial solution means det of A equals to 0, right? Now, what does that mean? Now, let's write the A part here. The A part will look like this: 1, A, B, 1, 1, right? C, C, 1. This is your A matrix. Now, det of A equals to 0. So let's take the det of this. Okay. So what I can do here is I can always compute some row transformations to simplify this further, right? I know that the det of A, to compute the det of A, because I want to make this det of A equals to 0. I want to make the det of this equals to 0. Let's make a bunch of simple row transformations or column transformations. Okay. So I'll make C1 equals to C1 minus C2. Okay. Look at this. I'm actually performing. Just a second. I think sorry. This is B1B. Sorry. Thanks again. My team is correcting me if I make a small mistake. Thank you. Yes, this is B. Yes. So if I make this, I'll do some simple transformations, simple column transformations. Just like elementary row transforms, elementary column transforms are also valid, right? So C1 equals to C1 minus C2. And if I perform C2 equals to C2 minus C3. Okay. See, I'm performing column transforms here. What would this result in? My column 1 is column 1 minus column 2. So this becomes 1 minus A. This becomes B minus 1. This becomes 0. I'm trying to make this 0 first. Okay. Next, C2 equals to C2 minus C3. So this will become 0 now. Okay. This will remain A. This will become 1 minus B. This will become B. This will become C minus 1 and this will become 1. Since I have some zeros here, now the det of this should be equal to 0. Since I have some zeros, the math will become easier. Okay. So now if I expand on this, what do I get? I get this very lengthy thing. I get 1 minus A, okay, multiplied by 1 minus B minus B into C minus 1. Okay. So this part is done. 0th part, I don't have to worry. I have the A part again, right? Plus A into, again, A into this part I have to worry. This part will anyway become 0. A into B minus 1 into C minus 1. Okay, this is the expression that I have. Let's try to simplify it a little, just for our sake. If I try to simplify it a little, what would I get? I'll get 1 minus A into 1 minus B, right? 1 minus A into 1 minus B plus, okay, yeah, let's try to write it in 1 minus B, 1 minus A, 1 minus C forms, right? Plus B into 1 minus A into 1 minus C. Again, I'm writing plus here because I'm making the C minus 1 as 1 minus C. Okay. Plus A into, plus A into, no. Let's change this. Okay. So if I simplify this further, how would this look like? So if I write it as plus, I can write it as plus A. I'll make this as 1 minus C and 1 minus B. So 1 minus C and 1 minus B. This is equal to 0. Okay. So this is what I have now. Now look at this. Look at this form. What do I want? I want A by 1 by A, B by 1 by B, and C by 1 by C. This is the expression that I want. what do I have? I have 1 minus a, 1 minus b in the numerator, 1 minus a and 1 minus c, 1 minus c and 1 minus b. So if I divide the whole thing, with 1 minus a into 1 minus b into 1 minus c, if I divide this whole thing by this, let's see what I get. So for this part, I'll be left with 1 minus c. Look at this. For this part, if you notice, if I divide the whole thing, because if you notice this, I have 1 by a, 1 by b, 1 by c in the denominators. I don't have those denominators here. But this is the problem that I want to solve. So I have to somehow try to translate this into this part. To do that, I'm going to divide everything by 1 minus a, 1 minus b, 1 minus c. In which case, what I'll get here is this. Okay, I'll get 1 by 1 minus c plus b by 1 minus b plus a by 1 minus a equals to 0. And the whole reason I have done this, by the way, the whole reason I'm dividing this is because this is the question that we are being asked, right? That's why I'm trying to divide this and so as to get it into this neat form. But if you notice, this b by 1 by b is matching, a by 1 by a is matching, but I need c by 1 by c. That is not matching. Okay, so let's actually write this one as 1 minus c plus c by 1 minus c plus b by 1 minus b plus a by 1 minus a equals to 0. Okay, minus c plus c. So I can write this as 1 minus c by 1 minus c, which is 1, plus c by 1 minus c plus b by 1 minus b plus a by 1 minus a equals to 0. Now this is the expression that we care about, right? This is 1. So if I take it to RHS, this will become minus 1, right? That's what it will become, right? This is 1. So what I want is c by 1 minus c, b by 1 minus b, a by 1 minus a, right? So this is equal to minus 1. Again, this is slightly tricky, but as long as you are patient with solving this expression, okay, as long as you're patient with this, you'll be able to crack this problem. And this whole column transforms, I've performed these column transforms so that this expression becomes smaller. I try to make as many zeros as possible. Okay, so and again, I'm trying to get it into this form of 1 minus b's, 1 minus b's, and 1 minus c's, and 1 minus a's as much as I can. Okay, because that's the form that I have, right? See, you should always take the steps based on what you have to eventually solve for. That's a very, very important part of solving mathematical problems like this. Okay, these are tricky, but these are doable if you're patient and if you're persistent. Okay, so let's go to the 13th question now. Okay, so this is okay, you can read this whole question. This is a lengthy question to read, but I've read it multiple times. Okay, so the contest rules that it is talking about, these contest rules that it talks about, again, please read this question in detail. I don't want to spend time here reading the question. Basically, these contest rules are nothing but your elementary row transforms. Okay, these contest rules that we have here are nothing but your elementary row transforms. Okay, that's how this problem has been designed. Okay, these rules are nothing but elementary row transforms, and the matrix that you're given is this 2 3 4 5. Okay, let me actually write it down on a fresh piece of paper here, because this is going to be slightly lengthy mathematics. Okay, so 2 3, let me give some space between 4 and 5. 2 3 4 and 5, 3 4 5 and 6, 4 5 6 and 7, 9 10 11 and 12. Okay, so the final question here is maximum number of teams that can win the contest. And the winning the contest basically means all of these columns have to become 0 for each team. Okay, so this row represents, each of these rows represents teams, and they want to make these values 0 by performing elementary row transforms. This is like a intricate problem which has been set out to test if you know how to perform elementary row transforms. That's all there is. Okay, so let's start performing some elementary row transforms, right? So I'll try to make row 3. Okay, so let's try to make this equals to 0. Okay, so row 3 equals to row 3 minus 2 times row 1. Okay, similarly, I have row 4, because this is a multiple of 3. I'll try to write it as row 4 equals to row 4 minus 3 times R2. Okay, see, I'm trying to make these two values 0. Okay, if you try to make these two values 0 using this, because 4 is a multiple of 2 and 9 is a multiple of 3. Okay, so you'll get this value 2 3 4 and 5, 3 4 5 and 6, So twice of this minus this, right? So what will I get? I'll get 0, I'll get -1, -2, -3. I'll get 0, -2, -4, -6. Now, first thing that you have to realize here is this multiplied by this is this. So I can actually make this 0 very quickly. Okay. Again, let's do a bunch of operations now. Okay. So on this, what I'll try to do here is I will try to make, so let's say I make row 1 equal, okay, let's try to also resolve these two rows. Okay, so let's multiply row 1 with 3, row 2 with 2, because this is 2, this is 3, right? Let's multiply this with 3, let's multiply this with 2. Okay, so the operations that I'll perform are row 1 equals to 3 times row 1. Okay, row 2 equals to 2 times row 2, and I'll make row 4 because I want to zero this out, right? Row 4 equals to row 4 minus 2 times row 3. Okay, when I do this, what happens now? 6, 9, 12, 15, 6, 8, 10, 12. Sorry, 6, 8, 10, and 12. 6, 8, 10, and 12. 0, -1, -2, -3. 0, 0, 0, 0. Okay, so the fourth team's values have become 0. Okay, but there is a fun part here, which is now if I perform row 2 as if I perform row 2 as row 2 minus row 1. Okay, let's assume I make row 2 equals to row 2 minus row 1. Now what do I get? Again, I'm just trying to make as many rows as possible as zeros. Okay, that's what I'm trying to achieve. So what will I get? I'll get 6, 9, 12, and 15. And I will get now, I'll get 0, -1, -2, -3. 0, -1, -2, -3. 0, 0, 0, 0. Now if I add these, if now if I perform row 2 minus row, sorry, row 3 minus row 2 as row 3, what happens now? I get 6, 9, 12, 15. 0, -1, -2, -3. 0, 0, 0, 0. 0, 0, 0, 0. Now I could not further I could not make this row 0 completely using just this row. Okay, I couldn't do this because if you look at this, this is 9 times, while this is 6 times, while this is 5 times, and this is anyway 0 times. Okay, 0 into 6, like whatever I multiply 0 with, I can't get 6. But if you look at this part, right, if I multiply this whole row with 9 and add this up, okay, then I'm going to get into a problem because this multiple is 6, this multiple is 5, and these two have become already zeros. So at most I can have 2 rows or 2 teams whose scores will become 0. I cannot further decrease it, whatever you try. Okay, so actually, so that's what this whole problem boils down to. It's just an intricate problem that is set up to make sure that you understand elementary row operations, and the objective is to use row operations to make as many rows as possible as 0. Okay, and it says how many maximum number of rows can you make 0? Only 2 rows you can make it 0. You can't make all the 4 rows 0, whatever you try. You can't even make the third row equals to 0. Okay, so now let's go to the 14th problem. Okay, so this is an interesting problem. Suppose that A is an n cross n matrix where A square plus NA equals to I. Okay, so what does it say? It says A square plus NA equals to I. Then A is it symmetric, involutory, idempotent, or none of this? Let's try to figure it out. I can write this as A plus NI, right? I can write this as this equals to I, right? I can write it this way, right? Now, if you take the debt on both sides, let's take the debt on both sides now. What does the debt on both sides basically mean? Debt of A into debt of A plus NI equals to 1, right? Now, look at this. The moment you have debt of A equals to 0, okay, the moment you have debt of A into debt of A plus NI equals to 1, what does this imply? This implies that debt of A is not equal to 0, which means A is invertible. A is invertible, right? But I don't have the invertible option anywhere here because I could construct a symmetric matrix which is non-invertible. I can also see I can construct all of these. So the right answer here, the right option would have been, is A invertible? That option is not given to me. So none of the above is the option here. Okay, is the right answer in this case. Again, a very simple problem, very simple determinant. We just applied simple determinant based operations. right? Okay, this is a good question. Actually, this requires us to know something called as Camus-Hamilton's theorem that we'll discuss in the next video itself in the course. But anyway, let me tell you what the theorem is, right? So let P be a matrix whose characteristic equation is this. Okay, then which of the following is true? The Camus-Hamilton's theorem, okay, what it says is this: the matrix whose characteristic equation that you have. Suppose I have a matrix P and whose characteristic equation is this, right? So if this is the characteristic equation, sorry, this is the characteristic equation. So what this theorem says, again, we'll show that, we'll discuss about this in the next video in the course, which we'll upload on Monday. But anyway, since this problem is here, let's solve it. It's a very simple theorem. Okay, what it says, to understand it, it's very simple. What it says here is, if this is the characteristic equation, if this is a characteristic equation of a matrix P itself will satisfy this characteristic equation, which means I can write P power 4 plus 2P cube. So instead of X here, okay, instead of X in the characteristic equation, or instead of lambda in the characteristic equation, if I just place P itself, okay, if I just place P itself, okay, if I just place P itself, okay, the matrix, so what this theorem says is that the matrix itself satisfies the characteristic equation of the matrix. That's what it means. Okay, now look at this. If this matrix satisfies this, you're given 4 options. Okay, let's look at this. Very simple. So can I write this? Look at this. Can I write this as P into P cube plus 2P square minus 7, because I can take the P out, right? Minus 2 equals to 0. That's what this is. Now P into something else equals to 0. Now if I take the det on both sides, okay, det of this into det of this equals to 0, because the det of a 0 matrix is 0, right? Here 0 is basically means the 0 matrix, not the scalar 0. Okay, because this will result in a vector for, so this will result in a matrix for us. Okay, the moment det of P into det of this expression equals to 0, what does this mean? This means det of P equals to 0, right? Because there is a constant here. Look at this. There is a constant associated with this. I'll have to actually write it as 2 into I. I should actually write it as 2 into I. Okay. So now what happens is, what does this imply? This implies that det of P equals to 0. If det of P equals to 0, then P inverse does not exist. So option D is the right option. Okay. This is a very, very simple application with simple algebraic transformations. If you know this theorem, you just place your P instead of X in this expression. You simplify it to show that det of P equals to 0, which means P inverse does not exist. Again, we'll discuss this theorem in detail in the next video in the course itself. Okay. So I hope, again, it is by design that we gave a slightly harder problem set this time. Let me just change to camera. So it is by design that we gave slightly harder problems. To be honest with you, some of these problems took us also some time to solve. Okay. So please don't get demoralized, because we want to expose you to a wide spectrum of problems. If you recall the last practice test, we gave very simple problems. Okay, that's to encourage people so that they don't lose motivation. But I can't keep giving you simple problems. Then you'll not be prepared for a hard GATE exam. Okay, so we want to stretch you, push you, and pull you. Sometimes we'll give you easy problems, sometimes we'll give you harder problems, thereby preparing you for all cases, whether you get a hard paper or an easy paper. That's our whole objective here, to be honest with you. We get nothing by giving you a hard question paper, to be honest. Okay, so that's the objective here. And again, those of you who are here, I just wanted to recap what I discussed. Let me just go back to that notes. So this is something that I announced at the very beginning of this session. So for all the registered students right now, by 29th, which is the Monday, we'll be done with linear algebra. There are 2-3 concepts like diagonalization, like LU decomposition, and the Hamilton theorem there. We'll finish all of that on 29th. 30th we'll leave for revision. Please revise all the concepts in linear algebra. I've also seen some very interesting questions from you. I'll touch upon a couple of them. The third thing is on first and second, we'll give you one subject test. Because linear algebra is a smaller part of the larger engineering mathematics, we thought one subject test is good enough. We don't want to overwhelm you there. Okay, please finish that. From 3rd to 15th, we will cover aptitude. Already 6 out of 9 chapters for aptitude are already uploaded to the course. For all the registered students, it's already uploaded to the course videos. Please go through them. Again, we'll have live sessions. We'll give you the detailed schedule, day by day schedule for aptitude also. And the reason we're taking a break from engineering maths and doing aptitude is because a lot of our registered students who have exams right now have requested us not to cover too much mathematics because they enjoyed some of the linear algebra topics, especially the geometric intuition, and they said they would want to follow with us. They're just not able to follow because of exams now, and we respect that. We completely appreciate that feedback that they've given us, and hence we are doing aptitude, which they, during their exams period of time, which they may not be able to follow, but once the exams are over, during their vacation time or during the summer break, they can quickly cover those topics. Okay, they can do it in parallel to other subjects also, because aptitude in GATE is very, very easy, to be honest. And starting from May 16th, we'll continue with our engineering mathematics and discrete mathematics. So we'll start with some of the simple topics in calculus, the functions, sets, group theory, monoids, all the beautiful algebraic structures. Then one of my favorite topics, which is counting and probability and statistics. So we'll try and finish all of the topics in engineering mathematics. Of course, in discrete mathematics, we have more topics like graphs. So we'll cover all of them. So from May 16th onwards, I strongly recommend and I strongly request you that we have to put in more effort, because that's a vacation time, because we are not putting too much effort right now. If you have noticed, for the last week also, we're only giving smaller amounts of content, and we're stretching this a little because we don't want to overwhelm students during exams time. But from May 15th, we will have to do it much, much faster, because we want to finish all the content as soon as we can and have ample time for practice once all the content is done. Okay, sounds good, folks. Any questions you have, any issues that you have, please reach out to us over email or phone. Any questions? Okay, we are here to help you through that process. Please reach out to us. Thank you for joining in. And sorry, I've stretched this session a little longer than the regular sessions, but I can't help it because we have slightly trickier problems. Again, there is one interesting question that came up in the that came up, which is why didn't you give us the geometric intuition of transpose? Okay, actually, I want to do that, but there's a small problem. The geometric intuition of a transpose of a matrix requires you to understand a slightly advanced concept called as singular value decomposition. Okay, which is typically not there in the GATE syllabus. Okay, again, I learned singular value decomposition when I was pursuing my master's. Okay, the easiest way to give the transpose, the geometric interpretation of transpose, is using the singular value decomposition. Again, it's not part of GATE syllabus, and I don't want to just cover random topics that are not in GATE syllabus. That way, we can spend a whole 6 months just doing linear algebra, right? I don't want to do that. But hold on, it's okay. But you understood, I hope you understood the meaning of transpose of a vector, right? See, we have used the concept of transpose of a vector to compute the dot product, right? If you have two vectors like this, we saw that we can use the transpose of one vector, okay? And if I can multiply with the other vector through the simple dot product, right? It gives me with some constant, right, which is the length of the both vectors. It will multiply with the cosine of the angle between them. So for now, the simplest way to think of dot product, or the simplest way to think of transpose, is it results in the cosine of the angle between the two vectors that you're multiplying. That's the simplest way to think about it right now. But the matrix inverse is slightly tricky. You would need to know some advanced concepts in linear algebra to understand it. It's okay when you go to a top university, and if you pursue areas like machine learning or AI, you will end up doing lots of linear algebra stuff where you learn all of these concepts. Again, singular value decomposition is something that I have personally used as a machine learning scientist many, many times. Okay, it's a very, very foundational concept. It's not there at undergraduate level, and it has some relationships with eigenvalues and eigenvectors that we have studied. Okay, singular values and singular vectors have some relationship with eigenvalues, eigenvectors, but I don't want to go into the depths of it right now. Okay, so just understand that there are some concepts for which giving geometric intuition is not trivial. Okay, there are some concepts where it takes a lot of time, or it requires some advanced concepts to understand the geometric interpretation. So for those concepts, I have intentionally skipped, because I just don't want to spend all the time solving linear algebra or explaining just linear algebra, right? We have tons of other stuff to cover. But please be patient. And by the way, if any of you find a good resource that I'm not aware of, please share it with me. I would love to share it with all the students. Please put in the comment section of the videos. We'll upvote it. We'll give it an admin vote so that other students also benefit from it. Okay, we want our students to contribute some great, like 3 Blue 1 Brown, right? It's a terrific resource. It's a brilliant resource with great animations. If some of you encounter brilliant resources like that, please share it with the whole community so that everybody benefits from it. Okay, thank you, folks. Thank you for joining on a weekend, and see you next Wednesday. Okay, have a good weekend. Take a break. Spend some time with friends and family, and see you next Wednesday. Bye bye.